Welcome and greetings to everyone. Today our group will be presenting about uranium mining issues, benefits, challenges and future perspective. First of all, let us introduce what uranium is. Uranium is a naturally occurring radioactive element that can be found in rocks and soil. Due to its radioactive properties, uranium is widely used as the main fuel in nuclear power plants to produce electricity. Uranium mining refers to the process of extracting uranium-containing ores from the earth. After extraction, the uranium ore will go through several processes to produce uranium fuel that can be used in nuclear reactions. This topic is important because uranium is one of the key resources that supports nuclear energy production. Although nuclear energy can provide a large amount of electricity, uranium mining also creates several concerns, especially related to environmental and health impacts. From the perspective of modern physics, uranium mining is closely related to several important concepts such as radioactivity, nuclear decay, radiation, and nuclear fission. The discovery of radioactive elements like uranium contributed greatly to the development of nuclear physics. Uranium atoms have unstable nuclei, which means they can naturally release radiation through radioactive decay. Besides that, uranium is also important because it is involved in nuclear fission. In nuclear power plants, uranium atoms can split into smaller nuclei and release a huge amount of energy. This energy is then converted into electricity. We chose this topic because uranium mining shows how modern physics concepts are applied in real life. It connects the theories we learn in physics with practical uses in energy production and also highlights the challenges that come with using nuclear technology. To prepare for this presentation, we gathered information from various reliable sources such as academic journals, scientific articles, and educational websites related to nuclear science. During our research, one of the main challenges we faced was understanding complex nuclear physics terms and finding a balance between the benefits and risks of uranium mining. To overcome these challenges, we compared information from different sources and focused on reliable scientific references to ensure that the information presented is accurate. Through this independent learning process, we gain a better understanding of how uranium mining contributes to energy production while also recognizing the importance of proper management to reduce its negative impacts.
To understand why we mine uranium, first, we must look at its atomic structure. Uranium is a heavy, naturally occurring element with highly unstable nuclei. Because these nuclei are unstable, they spontaneously undergo a process called radioactive decay to reach a more stable, energetic state. As you can see from the equation, the most abundant isotope uranium-238 undergoes alpha decay. It ejects an alpha particle which consists of 2 protons and 2 neutrons, transforming the uranium atom into thorium-234 while simultaneously releasing gamma-ray photons. During the extraction and handling process in mining, workers are exposed to 3 distinct types of ionizing radiation: alpha particles, which have high ionizing power but low penetration, beta particles, highly penetrating gamma rays. Understanding this specific decay chain is vital because it dictates the rigorous radiation shielding and ventilation designs used in modern mines to capture radioactive radon gas, protecting human health. While natural radioactive decay happens slowly over billions of years, modern physics allows us to artificially induce a far more powerful reaction using a specific isotope of uranium, which is uranium-235. The process is known as induced nuclear fission. When we look at the mechanics, a slow-moving thermoneutron is directed at a uranium-235 nucleus. The nucleus absorbs this neutron, briefly becoming highly excited uranium-236. Because this state is extremely unstable, the nucleus widely split into two lighter, more stable daughter fragments, typically barium-141 and krypton-92. Most importantly, look at the final terms of the nuclear equation. This split releases 2 or 3 free neutrons alongside a massive amount of energy. The secret to this energy lies in the mass defect. The total mass of the fission products is slightly less than the initial mass of the uranium and neutron. This missing mass is converted directly into energy according to Einstein's famous equation, which is E equal to mc squared. Because the released neutrons go on to strike neighboring uranium atoms, it initiates a self-sustaining chain reaction, which is precisely what we exploit inside nuclear reactors. So, how does this complex atomic physics apply to our daily life and benefit society? The primary application of my uranium is clean, large-scale electricity generation. The kinetic energy of the fission fragments and radiation is converted into thermal heat. In a nuclear power plant, this heat boils water into high-pressure steam, turning massive turbines to generate electricity that powers homes, schools, and heavy industry globally. To appreciate the sheer depth of this application, let us look at the data. Just 1 kilogram of uranium-235 can produce roughly 24 million kilowatt per hour of electricity. To match that output, you will need to burn approximately 2.5 to 3 million kilograms of coal. This incredible energy density means that uranium mining yields a fuel source capable of providing constant, reliable baseline electricity without emitting greenhouse gases like carbon dioxide or methane. Furthermore, from an economic standpoint, uranium mining fuels a robust industry that generates specialized engineering jobs and drives substantial national revenue.
Now, let's talk about the issues and controversies regarding uranium mining. We have to look on two major areas here, which is environmental risk and also health controversies. I will start with the impact towards environmental first. The first one is acid mine drainage, AMD. This happens when uranium ores are being exposed to water and air. Then, sulfides will oxidize, forming sulfuric acid. Sulfuric acid will dissolve heavy metals that flow into the water. This is how water contamination happens. Uranium mining also gives a direct impact towards animals, which they are facing acute toxicity, disrupting the reproductive cycle, loss of sensitive species, and degrading overall ecosystem function. In terms of air pollution, the dust at the atmosphere contains radioactive particles like thorium and uranium, which can contaminate the soil, vegetation, and surface water over considerable distance. For health controversies, it involves radiological and cumulative hazards, where alpha radiation from uranium isotopes is less dangerous externally, but when we inhale it, it will transfer to another organs, leading to a long-term internal radiation damage. And lastly, chronic disease. The exposure to dust containing silica and mining dust will contribute to the development of chronic bronchitis and emphysema. We have two recent developments here. The first one is the global shift to in situ recovery, ISR. This is a mining without digging technology, where the chemical extraction process that not involve moving huge amount of rocks, and widely used in countries like China, Australia, and also Russia. The advantages are minimizing the land disturbance since there are no waste or pits dump created, and can protect the water security through close-up process that can prevent chemical leakage. As we can see in the picture, there are 3 steps involved, which is the injection of weak acid like sulfuric acid, dissolution, and lastly recovery, where the pregnant solution is pumped to the surface and treated by ion exchange and precipitation into yellow cake. And the second development is the uranium extraction from seawater. The seawater has massive amount of uranium, but it's scattered in tiny amounts. So the metal organic framework MOF as an adsorbent with higher selectivity and absorption capacity to capture the uranium ions. The advantages from this development are almost unlimited supply because the ocean contains tons amount of uranium, and it also provides fuel for nuclear power plants in the future and less damage to the land compared to the traditional mining. But the challenges are time consuming since uranium is spread out in very tiny amounts, highly cost, and scientists are still figuring out on cheaper technology before it can be used widely around the world.
Besides producing nuclear fuel, the uranium mining industry also offers many career opportunities for graduates with science and engineering backgrounds. For example, nuclear engineers design and improve systems used in nuclear energy production. Mining engineers are responsible for planning and managing mining operations while ensuring efficiency and worker safety. Another important role is the health physicists and radiation safety officer. They monitor radiation exposure, make sure safety standards are followed, and protect both workers and surrounding community. In addition, environmental scientists assess the environmental impact of mining activities and develop strategies to minimize pollution and restore affected areas. These careers work together to ensure that uranium mining is carried out safely, efficiently, and sustainably. To succeed in these careers, professionals need both technical knowledge and draw interpersonal skills. From the technical aspect, they must understand nuclear science, know how to monitor radiation levels, analyze data accurately, and evaluate environmental impacts. These skills help ensure mining activities meet strict safety and environmental standards. Soft skills are equally important. Critical thinking allows professionals to make informed decisions, while communication and teamwork are essential because mining projects involve experts from different fields. Problem-solving skills are also needed to manage unexpected challenges during activities. Since nuclear technology continues to advance and safety regulations are regularly updated, continuous learning is necessary throughout their careers. Although mining uranium provides many benefits, it also comes with several important challenges. One of the biggest challenges is handling radioactive material safely to minimize radiation exposure. Companies must also comply with strict safety regulations to protect workers and the environment. Another challenge is public concern about environmental and health effects of uranium mining. Therefore, mining companies need to operate transparently and adopt responsible mining practices. To overcome these challenges, workers receive regular safety training and follow established radiation protection procedures. At the same time, new technologies and sustainable mining methods continue to improve safety, reduce environmental impacts, and increase public confidence. In conclusion, uranium plays an important role in supporting nuclear energy, which provides a reliable source of electricity for many countries. At the same time, uranium mining contributes to economic growth by creating jobs and supporting industrial development. However, because uranium is radioactive, mining activities must be carefully managed to protect both human health and the environment. By applying sustainable mining practices, following strict safety standards, and embracing technological innovation, the industry can continue to meet global energy demands while reducing its environmental impacts. Thank you for your attention.